The first plenary talk today is by Alexandru Aleman from University of Lund. He's going to talk about generalization of the Branges-Rovnyak spaces. Alexandru, please.
Thank you so much for inviting me. It's great to see you guys. This is joint work with Frey Dalin, which is my student, PhD student, and Bartosz Malman, who used to be my student, but then he finished. He's in KTH in Stockholm now. And what I essentially want to show you is there are a number of generalizations of the Branges-Rovnyak spaces. So the definition was already given by Dan. I would like to show you some of these and tell you why these have been introduced and what are they good for and what was the idea behind that. There aren't so many, but then I'll recall the definition. See, this is the easiest via the reproducing kernel, which is the one that Dan also used. So you take a function bounded by one, analytic in the disk, and then you look at this type of kernel. Then he also told you an equivalent definition, namely the h of b, the Branch space, Rovnyak space is just a range of this defect of a Toeplitz operator, which is endowed the way ranges of operators are endowed. So these are the definitions. And then, like Dan was saying, I mean, both, if you look at these definitions, it's not so clear how to find functions in the space. And this is one of the main difficulties. I will say a few words about it. I don't have a new recipe how to find functions in the space, but when we want to prove theorems about these spaces, this is one of the problems we encounter. So, yes, let me also, this is probably Dan's lecture from tomorrow. So according to this B, there are two types of the branch spaces in the sense that they have very different properties. So if this integral is finite, then B is, so to say, not an extreme point of the unit ball, which is not so big, important for what we're talking here. But then h of B starts to be more similar to the Hardy space itself, in the sense that you can multiply, you have a forward shift acting on it, you have polynomials in the space, they form a dense subset. These are all things that you can find in Sarason's book. While if this integral is minus infinity, then B is an extreme point of the unit ball. Then h of B starts to resemble more to a k theta, to a model space. So then the properties are quite different. Well, it cannot contain polynomials, but surprisingly enough, in all cases, h of B will contain functions which are in H2, but also extend continuously up to the boundary, the disk out. Now, this is something which is not so trivial. It is not so clear how to prove that such functions exist. Given an h of B space, find by a formula a function which extends continuously up to the boundary. This is not a simple problem. However, there is a qualitative approach, which is due to Alexandru for model spaces. 1981, Alexandru has a duality, very clever argument to show that the functions which extend continuously up to the boundary form a dense subset of h of B in the case when B is in. And then myself and Bartosz Malman could extend this to the general case for general B much later. Now, the way to start the argument is the same as Alexandru's, except that when you get to the technical part, then his proof has to be changed, because B is just a general bounded function rather than an inner one. And indeed, you have to do something which is not the same. So indeed, yeah, you have to think a little bit about this. However, it's a beautiful thing that you have such functions in the space. On the other hand, construct one, this remains a difficult problem. And I know there are people, and I'll tell you later, there are people working on this. I mean, this constructive aspect is very important, I think, in such spaces. So just but at this stage, it is kind of not so well understood whether how to construct such functions. On the other hand, it's very good to know that there are depths in the space. Well, what's a common property of all H of B spaces? Again, Don said it. They're invariant for the backward shift. So mine is called L, Don was S star, but it's the same operator. So it's the adjoint of the shift. More than that, this L is a contraction. And finally, I assume that B of 0 is 0. I will assume it all throughout the talk. We can do the other case as well, but it's much easier for me to assume this. So in that case, the producing kernel is constant at 0. So maybe I should, I mean, if we go back, well, I think you've seen the producing kernel. So if B of 0 is 0, when you put W is 0, you get 1. Right? So these are the three common properties of the Branges spaces. And this was the departing point for Bartosz and myself. We said, well, why don't you have a look, don't we have a look at spaces with this property? And it's actually worthwhile, because if you can show that if you have these three properties, so in the opposite direction, then the kernel is somehow similar to the Branges-Rovnyak kernel. So here is the result. So if you have any reproducing kernel Hilbert space analytic function in the unit disk, such that, what did I do now? The backward shift is contractive. The kernel at 0 is constant, I mean 1, so they normalize at 0. Then the kernel will have this form, but now B is analytic bounded. It's just its values are sequences, L2 value. This has to be like this because, yeah, the class of these functions of these spaces is way wider than the Branges-Rovnyak space. But this is one generalization which just comes from these three properties. And I want to show you what you can do with this. But before I show you that, let me tell you why is this proposition true. I'm not going to give the whole proof, but just want to convince you that it's not very difficult. It's kind of typical working with kernels. So you start with a contraction. L is a contraction, right? And then this means LL star is a operator is less or equal to 1. So identity minus that is a positive operator. Okay. And now if you apply positive operators to kernels, you get another kernel. Well, a positive definite function. Well, if this is so, then kernels can be represented. I think Dan had this representation of kernels as well. Some people call this the Kolmogorov representation of kernels, but is I mean, the entries of B, you should think like choosing an orthonormal basis in the space where with this kernel here. And okay, you have this representation, but the thing is that the left-hand side here can be computed in terms of K. Well, if you can compute it, it's like getting an equation for K. And we replace it above and solve for K, and then we get the proposition. So it's not something extremely sophisticated. I'm going to continue to call these spaces age of B, but now B is allowed to be a sequence, a vector. And Bartosz and I, this is very recent years, we decided to study them somehow systematically. It's one thing that occurred to us is that if you have only finitely many non-zero components in the vector B, then the space that we get with such a kernel is actually very similar to the Branges-Rovnyak space. Again, you have two types, extremal, non-extremal, and you can study them. It's a lot of similarity to the scalar case, right, with one component. Now I think I wrote here, yes, this happens exactly when identity minus this LL star has finite rank. So that's exactly when you have finitely many non-zero components here. Now, if you have infinitely many components, then we're very far, might be very far from the Branges-Rovnyak spaces, because the Dirichlet space, the more sophisticated versions of the mu spaces, if you're familiar with that, basically any space where the forward shift is expansive will give you an example of such an age of B with B a vector. So this is really, oh, sorry, again, the kernel has to be normalized. But you see that the class of these things is huge. And indeed, technically, you do realize when you work with an infinite sequence here, you encounter serious problems, because which is just certain limits or certain infinite matrices which appear in the arguments, and they're difficult to handle. So, but that's to expect, because here's a huge class of spaces. However, Bartosz and I were able to prove the same theorem extends to this context as well. So if you have a vector here, still you always contain a dense set of functions which extend continuously up to the boundary. About the proof of this theorem, I should say that this is somehow you have to do something else. You can then for for a scalar case. So if B is a scalar, okay, there are some classical theorems that you can use, but if you have a vector here, then the method has to be changed. So we really have to work for this theorem. So, but still, it's interesting that such a theorem continues to hold in this generality. I want to tell you a few words about its proof, because the method somehow is, again, it's about finding some information about the norm in such a space, H of B. And here's what you can do so basically what I'm going to say is essentially this Nag-Voyage model for the contraction L, first, acting on H of B, is a little bit, well, to expect. It's easier than for an arbitrary contraction. And if you use that, then you get a very useful formula for the norm. I'm going to show it only in the scalar case. So let's say we are in the Branges-Rovnyak space. And then I just consider this direct sum. H2 plus L2, this, see if this is a non-extreme thing, I could put just to close the polynomial here if I wanted. But if B is extreme, well, then this is indeed, this measure here will not give point evaluations in the D. So it's a quite different thing. However, in this space, we consider a shift invariant space, which take H2 and multiply with this B and 1. Okay, this is obviously closed. I mean, it's very easy to check that this is a closed subspace. And then what we observed is that for H of B, you have an isometric map of this form into the ortho complement of M. In other words, is what you do is you take your function, which is an analytic function, an H2 function, in H of B, and then you look for a mate to make you orthogonal to this subspace. And then the norm of our function in H of B is just the norm of F squared plus the norm of G squared. This resembles a little bit to the formula that Don had with the H of B bar, but this is a different interpretation that I'm giving here. I never thought if one could reduce, what's the connection between the two formulas, but they might be quite close to each other. But anyway, this is, as I said, essentially is the Nag-Voyage model because then you represent L basically like a backward shift on a model space, which is vector value now. Okay. Now the question is, okay, you can prove that these spaces contain functions which extend continuously up to the boundary. Unfortunately, we cannot construct them, but just show that they are dense. But then I think it would be natural to ask whether you can approximate by a smoother function, so maybe C1 or C2 or whatever. Now, I think this is a quite subtle problem, even for model spaces. So the answer is no in general. So even for a model space, could be that for certain inner functions, you cannot do this. And there was work of Diakonov and Dima Kavinson on this, but very recently, Bartosz and Adem Limani have made considerable progress in this direction. So they have so Bartosz will speak here and he will speak about this. So I'm really looking forward to that. I think their results are really interesting and very nice. Okay, but now let's go to another generalization, which is the so-called SubBurma spaces. Now, SubBurma spaces, these were introduced by Kehezu, but it's again a very natural generalization. So here's, let me recall that the H of B kernel looks like this. And then Kehe in 1996, yes, introduces the Subburma space H0B. I will have an H alpha of B, so don't be so. So it's okay. I hope the notation is it's H0B. It's a different space. The kernel is now has the form 1 minus B of Z B of W bar divided by the square of this. So in other words, instead of the Cauchy or Serge kernel that you use to define the Branges-Rovnyak space, you use the Burman kernel here. So that's why Kezu called it Subburma Spaces. So B is again bounded by 1, analytic in the distance. Okay, so this is 1996. For some reason, I prefer this notation L2A for the Burma space. And here again, you can play exactly the same game. So if you denote TB, the multiplication by B, then this H0B is nothing else than a range space. Endowed, as we had in the Branges-Rovnyak case, with a scalar problem. But now, this is quite different from the Branges-Rovnyak space because, for example, if you do what in Don's notation would be H0B bar, in my notation, you just change TB star to TB star TB, okay? Then you get the same thing, which is, well, for example, if B would be an inner function in the Hardy space, then this will be 0 and this will be the Branges-Rovnyak space. But this is true for any B in the Burma space case. Then this H0 of B is both forward and backward shift invariant. And the multipliers are H infinity. Any bounded analytic function will multiply H0 B into itself, which is in some sense saying that, yes, this is a fairly big space. Okay, but now, yeah, let me, this was what I find attractive to this SubBurma Spaces is the relation to Shimorin's work. Namely, see, in the previous slides, I extended or generalized the Branges-Rovnyak spaces by saying that, well, I use an operator inequality, namely that the backward shift L is contractive, norm L is less or equal to 1, right? And that was the generalization. But I can do exactly the same thing, except that the inequality I'm going to use now is more sophisticated than that, and is due to Sergei Shimorin. The regretted Sergei Shimorin, and it is essentially related to his approach to Berling theorem for the Burma space. So here's what the result says. So suppose that we have these properties which are essentially like in the SubBurma case. So we have a kernel which is normalized at the origin. This is not a really important thing, but let's say that this is so. We are backward shift and forward shift invariant. So this is the set. But then you get this form of the kernel, which is the generalization of the SubBurma kernel, if and only if in our space we have this inequality. Now this is a little bit subtle. You see, you have the forward shift on F and nothing on G, and here we have twice nothing on F and the forward shift on G. It is very remarkable inequality. As I said, this led to an alternative approach to Berling's theorem for the Burma space, but it's per se a very interesting thing. Again, you don't get a SubBurma kernel, but something which is quite similar. You get again a vector valued function b, which is analytic, is bounded by 1, but it is vector valid. Now, the proposition itself is, again, when you're used to kernels, maybe not so difficult, but it is quite a nice idea. It's a little more complicated than, than the previous one with the backward shift. So now this should be a capital T. We have a capital T from the sum of 2 copies of H into H, but multiplying the first component with Z forward shift and adding the backward shift applied to the second. And then the inequality that I had can be easily modified with this assumption here to show that the norm of T is not more than square root of 2. In other words, twice the identity minus TT star is positive. But then as before, this TT star applied to a kernel can be computed. So we write that this is, we write being positive definite means that it has this form. And again, we can solve for K. That is a beautiful idea. I liked it very much. It's due to Scott McCulloch and Stefan Richter. That was unpublished. But then a number of years after that, together with Håkan Hedeman, we wrote an overview paper about progress in problems regarding Subburma spaces, and we have included it. But the idea is from the two, Scott and Stefan. Yeah, this is a very nice. Sergei Shimorin's approach was a little more different. Essentially, he used the Burma norm and Green's formula to prove this inequality, and then he realized how powerful it is. I mean, this inequality. But yeah, okay. Then recently, Cheng Chu, I think, proved that polynomials are dense in this Subburma space. This is somehow reminiscent from the Berling-type theorem because, I mean, the way to do it, and this is, I pretty much follow, I think, Scott and Stefan. So you just see that the reproducing kernels are in H infinity, right? Because, well, let me show them to you again. Come on. If you fix W, then obviously this is an H infinity function. Okay. But H infinity is continuously contained in this space. In fact, they are multipliers, and then you convince yourselves that weak star convergence in H infinity implies weak convergence in the Subburma space. And then you take an H infinity function or a kernel approximated in the weak star topology with polynomials, and then you get approximation in the weak topology in A0B. And yeah, so that would be an alternative approach to that's the avoidance. But this will be an important topic here because I'm going to come back to this in a moment. Okay. I don't know what I did here, but this is H0B. Many properties continue to hold for the spaces H alpha of B, which is just, I'm using here a different Burman kernel. This is a weighted Burman kernel. Alpha in general should be bigger than -1, but most of the results are valid for alpha greater or equal to 0. But yeah. Now, one thing that's happening with this alpha greater than 0 is the lack of an operator inequality. So we cannot characterize, at least I cannot characterize these kernels with an operator inequality. This is again, I would say, a difficult thing. If there is an analog of Sergei's inequality for these kernels, it will look very different, simply because in weighted Burma spaces with this positive alpha, well, let's say when alpha is bigger than 1, then Berling's theorem fails, and even for the simplest invariant subspaces, and the analog will be have to register that somewhere. So it will be a very complicated statement. At this moment, we don't have. I think we're very far from having analogs of that. Okay, but people showed a lot of interest for other properties, not for the inequality. So Ali Apkar and Jafar Zadeh, 2010. So this is quite a recent work. Maria Novak, Rososchuk, 2014. And then another interesting result of Rososchuk and Sim-Sak last year, they consider similar kernels also in the unit ball of CD. I don't know, well, this would be complex, yeah, several complex variables. I'm sorry that, yeah. So this is quite interesting that you can, this inequality that H0 of B or H alpha of B equals H alpha of B bar, or if you want, this attracted a lot of attention and people worked on this. Not on density of polynomials, that's a different issue. Okay, now I want to propose another generalization which actually contains the previous ones, but of course will bring us in a fairly general context, and maybe there are some certain things, maybe too general, right? Okay, so here's what I want to do. So we take, let me introduce first the Nevalina-Pick, complete Nevalina-Pick kernel on some abstract set, which is just non-void, which is normalized. Now, my definition is a little bit dull. I'm just saying that this is a kernel of this form. Now, these kernels are defined with the help of interpolation, so Nevalina-Pick interpolation. And complete means that you interpolate matrices. And well, the normalization, then this is a theorem that if you can't solve those interpolation problems, then you will have this form. There is this beautiful book by Jim Agler and John McCarthy about this. But for our purposes, let's assume that this is the type of kernel we want to discuss. And recently, or at least for me, people looked at kernels with the property that you can divide such a normalized CMP and stay positive definite. So you're looking at, oh boy, and it's a kernel K with the property that there is a normalized CMP S, such that K over S, I'm very sorry, this H is a K, is positive definite. So looking at that. Why? Well, at least why I looked at it is I worked with Michael Hartz and John McCarthy and Stefan Richter in 2017. And we could show with kernel methods that Hilbert spaces with such reproducing kernels, functions in such spaces, they have a van Lina factorization, so they kind of can be represented as quotients of multipliers. Now, multipliers from where to where, this is more sophisticated, and I don't want to get into details, but I think it's a very interesting structure. And then was my curiosity somehow saying, yes, but once we perform this division, then we get another kernel, this K over S. So what can we say about that Hilbert space? That Hilbert space somehow involved, at least in the arguments. But if you do that, you get a type of kernel which generalizes everything what I showed here. So I'm just saying all kernels which we had here have this form. I mean, so I start with an S like this, and K is the one obtained by dividing S, right? So this is the, and now if you put K to be the Burma kernel, you get the Subburma kernel. If you put K to be the Cauchy or the kernel, then you get the Branges-Rovnyak spaces. And the weighted Burma space, then you get these other types of kernels. So from that point of view, of course, this is very general. And then there is a certain risk that it is too general, but not for certain topics. I think that what I'm going to say now here is that some of these results, which I mentioned earlier, can be derived from just very general properties of reproducing kernels. And here is kind of a list, or well, some of those which we could derive. So you don't need to have a specific Burma kernel here. You can put basically on any kernel. And I want to discuss three aspects here. It's fairly short. So this is what I'm doing with Fred Dalin, who is my student who started a year ago with me. And let me start talking about multipliers. So as we have seen, the multipliers of this H alpha B is the whole algebra H infinity. If alpha is greater or equal to 0. And this was the result of K in 96, but then the other people also extended it for other alphas. I should say that if alpha is less than 0, you can go up to -1. And -1 is the Hardy space, right? The Hardy kernel. Then I believe that the algebra is strictly contained in H infinity. At this point, I don't know how to prove it, but I'm pretty sure that this is what it is. Just don't see it. It isn't known. But here is how you can approach these multiplier algebras. These are simple observations. So suppose that you have a kernel which can be written as a product, right? K1, K2. And this 1 minus B, the scalar product of BZ, BW times K1 is positive definite. Then the multipliers of the other space of HK2 are contained in the multipliers of the HK of B. So then you get this multiplier algebra as a subalgebra of the multipliers of H of P. And this is basically everything. This observation proves that. And this actually very simple is just the sure product theorem. But we prove, I won't give the proof here, but as I said, if you have alpha greater or equal to 0, K1 is the Cauchy kernel, K2, this is a Burma kernel. And then you apply the proposition because the multipliers for HK2 is all of H infinity. Okay. In the other case where I don't know the exact result, in doing this, sorry for the misprint again, so +1 is in the power. But if you do this, then the kernel of this K2 or H alpha that you get is a kernel in a weighted Dirichlet space. Then the result only says the multipliers of this weighted Dirichlet space will be contained in the multipliers of H alpha B. So this is not, I don't know how sharp this is. Something like that could be carried over to the Branges-Rovnyak spaces, provided for certain B's. But yeah, I at this point I'm not so convinced that this will be interesting. Okay, so my second topic is about embedding. So again, you start with HK. So you should keep in mind that this case, the Cauchy kernel, the Burman kernel, weighted Burman kernel. And so this is the big space, right? And then you form this HK of B by multiplying with one minus the scalar product B of Z, B of W. And then Dunn had this in his lecture that this HK of B is contractively contained in HK simply because the kernel here is smaller than the kernel here. So but if the embedding is compact, could be, then you know, whenever you have a sequence in X such that the norm of the K goes to 0 to infinity, then the norm of the kernel age is the kernel here, will go to infinity. Well, it cannot go as fast. So divided by the K must go to 0. This is exactly compact because when you have the continuous compact embedding, the adjoint of that embedding maps kernel to kernel. So that one will be compact as well. And that's why this is happening. But this in our case just means that the B of Zn goes to 1 in norm, because then the norm here is just 1 minus the norm of B of Zn squared. So this is something quite restrictive. If you think, for example, take X to be the unit disk, and assume if you have a Burman kernel or a Cauchy kernel, then this will go to infinity whenever you approach the boundary, right? So then, for example, if B is scalar and you expect the embedding to be compact, then this only can happen when B is a finite Blaschke product. So the embedding will never be compact, except in this case. Now, in this case, we can basically prove that if the forward shift is contractive on the big space, so this happens in the Burma space case, in the Hardy space case, it even is isometric. And then for any finite Blaschke product, it actually turns out that this HK of B is nothing else than the HK of Z. So they're very simple. And then if identity minus MZ star is compact, and so it's embedding. And this recovers a number of results of this type. But it's just very general. Again, this is just says that that type of compact embedding is can be shown is not happening very often, and by using just general properties of kernels. Okay, then let me finish with approximation. Now I kept on talking about approximation by polynomials, and especially when talking about SubBurma spaces. But now I'm in a very general context. My kernel K lives on some set X. So instead of that, I'm going to investigate approximation by linear combinations of kernels instead of polynomials, which is for Berman kernels and so on is it's pretty much the same thing. But okay, and then to state a result, I use this definition of set of uniqueness if there are no non-zero functions which vanish on the set U. So 0 is the only one. And then also for notations, I consider B as a, instead of a sequence, I say it's a contractive multiplier from this tensor product into HK. And I denote by MB, the multiplication operator. Okay, and here's the theorem. So here's the hypothesis. So suppose in our abstract set X, we have a set of uniqueness such that there we can estimate the point evaluation, so to say, in terms of this identity minus MB star and BGG. So this is a technical hypothesis. This is still, we're not really done with this theorem, but well, okay. So, but this hypothesis is fulfilled in the Berman case, in the ball, and also in the non-extreme case of the Branges-Rovnyak, many others. And then HK of B contains all these kernels with W and U, and their linear span is dense. So this is a very general theorem about just a set. Now, if you go back to the disk or the ball, then you can use U to be the whole disk, the whole ball, and then this is equivalent to approximation by polynomial. So they will be dense in all of these spaces. So this will contain, of course, Sarason's theorem and Chu's theorem and many others from this type. But I'm still a little bit dissatisfied with this hypothesis. So maybe we should call it work in progress. This one is true. Okay, thank you very much. And
thank you indeed. Let's thank Alexandru. Any comment or question for Alexandru?
Sorry.
Please, Dan.
So in the first part, you alluded a little bit to some work concerning a constructive approach of finding continuous functions in model spaces or in H of B. So can you say a little bit more, or what is up to now?
So, Bartosz is going to talk about it tomorrow, but they well, I don't have anything written here, so it doesn't matter if I go back there. But the problem is really interesting. So for example, in the case of an inner function, right, in the model case, so suppose you have a singular inner function and you want to approximate with C1 functions, and then the singular measure, I mean, the conditions that you get are in terms of what they do on these Carlson sets, on the sets of finite entropy. So it's a really interesting interplay with, with Cora Bloom's work. And, but well, I don't want to spoil.
Okay, no.
His talk, but it's going to be very interesting, and then they can extend this to the H of B case.
Mm-hmm.
So in fact, they also have some very nice equivalent conditions. So a certain approximation is possible if and only if something is happening in a P2 mu space. So that's really surprising. I didn't expect. Well, You should look at the talk. It's I really like they did very nice work. Yeah.
This equally applies even to, I think, the last slide when you say reproducing kernels are dense. And it has been a question for me that in the most general setting, can we provide kind of constructive approximation scheme for functions, not based on polynomial, based on the reproducing kernel?
Yes. In this generality, it's probably quite hard. And, maybe if we have some more concrete things like Toeplitz operator and stuff like that, we can somehow approximate the identity. But in this case, at least I don't know. Yeah. It's certainly, these constructive things are so hard, but of course they are certainly very interesting. I mean, all these other arguments like Alexandru and all this very abstract functional analysis. So if you want to approximate a function, there's no help from that. It's only telling you that you can. Yeah.
Yeah, even in the, I mean, concrete cases, as you said, is not an easy question to provide a scheme, a constructive method to do so.
Exactly. Yeah. Yeah. No, I don't know that. Yeah.
Yes, Emmanuel.
Yes.
Hi.
Hi, Alexandru. So yeah, maybe I misunderstood something, but in the last theorem you mentioned, which is here in the slide, you said that you were not so happy with the hypothesis, but on the other hand, if I understood correctly, in the Branges-Rovnyak spaces, to have the kernel and the density of the Cauchy kernel in the space, you need the hypothesis that the function b is non-extreme, right?
Yeah, you're right, and this is so if you think that this g is scalar,
Yeah.
so you want that g to be the value of g at z to be less than this thing. But if you think it in the Burman case, this is like 1 minus modulus b squared.
Okay.
G squared. In the Hardy space, you get it only when you're not extreme. That's exactly when you get it.
Okay.
But well, the reason I'm not satisfied is that my feeling is that well, I don't understand this so well when b is a vector, is an infinite vector. That's my problem. It's not a scalar case. I do. Yeah.
Okay.
But yeah.
Thank you.
Yeah.
Any further question or comments for Alexandru? Well, if not, let's thank him again.
Thank you. Great to see you. Well, I'll see you again because